Hi everyone. So in this session, we will continue the discussion of weekly quiz 16 of group theory. Okay. So this is part 2. In the part 1, we have already seen some questions. Okay. So I can say question 1 to question 11. Those we have seen in the part 1. In this session, we are going to discuss the remaining of this weekly quiz 16. Okay. So let's start with this question. Question number 12. Now, let's start. So tell me, if G is a abelian group with identity element E, and this H is given to you, what is this H? In this H, we have those elements of G for whom x power 4 is equal to identity element. Now the question is asking which of the following is true about H. Okay. So the question is asking H is a subgroup, H is not a subgroup. Okay. So these things question is asking. So let's see. Let's see this. First of all, you tell me if you have a group. You have a group. Let's assume G comma star. This is a group. Then when can I say H is a subgroup of G? Then tell me what is the definition of H is subgroup of G? Remember this symbol means subgroup. So when can I say H is subgroup of G? I can say H is subgroup of G if and only if one thing, H must be subset of G. H must be subset of G. Okay, this is the one thing. Means H must be a subset of G. This is the symbol for subset. So H must be a subset of G. And second thing that H must be a group. That H must be a group. Okay, H must be a group. Remember now, if H is a group, then what are the things you need to check? What are the things you need to check? If H is a group, then you need to check that identity elements should belong to H. Okay, this is the one thing you should check. Identity elements should belong to H. Next, I can say it should be closure property must be satisfied. I can say closure property. And the next is inverse property. The next is inverse property. Do I need to check the associative property? Do I need to check associative property for H? Remember, this operation is already associative. This operation, because I am saying that you have a group. You have group G comma star. So remember, this star is already associative. Okay, this operation is already associative. So you don't have to check. This H will always be associative. Okay, remember this group G, because it is a group, so associative property is satisfied. So this star, this operation, this is already associative. So you don't have to check for associative property. Very simple, I can say you have a group. H is a subgroup. H is a subgroup. This is the symbol for subgroup. H is a subgroup. If and only if H is subset of G, in this H, you must have subset of elements of G. Okay. Next H must be a group. Okay. Means identity elements should belong to H. Closure property must be satisfied and inverse property must be satisfied. So we need to check these properties. Okay. Now let's see this H. So you have this G, which is abelian group. Remember, this is already given. This is abelian group. Means commutative property is satisfied by this G. Next, identity element is there. Now the question is asking that this H. First of all, you tell me, can I say H is subset of G? Can I say H is subset of G? See, remember, this group G is given to you. This group, this is abelian group. We have a G comma star. Okay, which is abelian group that is given to you. Abelian means commutative property. And this is a group. So this is abelian group. Now I am saying that I am defining this H. In this H, I have those elements of G such that x power 4 is equal to identity element. Okay. Now you tell me the one thing you tell me is H subset of G? Can I say H is a subset of G? Tell me, can I say H is a subset of G? This is the symbol for subset. Can I say H is subset of G? Of course, H is subset of G because in this H you have those elements of G. Elements of G you have in this H, right? H is a subset of G because in this H you have elements of G. Okay, in this H you have those elements of G for which x power 4 is equal to E. So remember, yes, this H is a subset, right? So this is a subset because very simple. In this H, remember in this H, you have elements of G. Very simple. In this H, what you have? You have X, which is element of G, and something. So you can notice that in this H, you have X. In this H, I have X such that X belongs to G. So you can easily notice X is element of G. X is element of G. Is this point clear? One thing, is this clear that H is a subset of G? Okay. So very simple. H is a subset of G. Is this point clear? Now let's see the second point. The second point. Now let's check, is this identity element in this H? Okay. See, this we have already checked. This one thing we have already checked, means H is a subset of G. This is done. Next, now we need to check, is this H is a group? Okay, this is what you need to check. Now the second thing you need to check is H is a group. So this is what you need to check. The second thing, what you need to check? You need to check, is H a group? This is what you need to check. Means what are the things you need to check? One thing you need to check is identity element belonging to H. Second thing you need to check is H closed? Okay. And third thing you need to check, is A inverse there? If A is there, then is A inverse there? Means third thing you need to check, for all A belonging to H, is A inverse also there? Is A inverse also there? In this H, for all the elements in this H, can I say A inverse is also there in this H? So these three things you need to check. Let's check them one by one. What about this identity element? What about this identity element? So tell me about the identity element. Can I say identity element will belong to H? Please tell me. Can I say identity element will belong to H? One thing you tell me, in this H, what are the elements? Very simple thing I'm asking. You have G comma star, which is abelian group. This G comma star, this is abelian group. One thing I'm asking, in this H, what are the elements? Look at this H. In this H, what are the elements? Like, when can I say this element? When can I say this element will be in H? Like, for example, if I give you some element alpha, when can I say? If alpha belongs to H, then what can I say about alpha? Then I can say that alpha power 4 is definitely identity element. Okay, yes or no? Because in this H, you have those elements. In this H, remember, in this H, you have those elements of G for which power 4 is equal to identity element. In this H, you have those elements for which power 4 is equal to identity element. Okay, so I can simply say that this alpha, if this is there, then it means alpha power 4 is equal to identity element. You tell me one more thing. If beta power 4 is equal to identity element, then can I say beta will be here? Can I say, if this happens, if beta power 4 is identity element, can I say beta will be in H? Yes, of course. Yes, right? Yes or no? So very simple. In this H, remember, you have those elements for which power 4 is equal to identity element. If you have some element, then it means power 4 is equal to identity element. Okay? Very simple. Very simple. If you have some element, if power 4 is identity element, then that element is there. Okay? If power 4 is identity element, then that element will be there here. So very simple. So first you understand what is H. In this H, you have all those elements whose power 4 is equal to identity element. Okay? So very simple. If your power 4 is identity element, then you are in H. And similarly, if you are in H, then your power 4 is equal to identity element. Very simple. First you understand what is H. Now, once that is clear, now you tell me, can I say E belongs to H? Can I say E belongs to H? For this, what we need to check? For this, you need to prove that E power 4 is that identity element. Yes, of course. E power 4 is identity element, that we already know. We already know identity element power anything is identity element. This we already know. Identity element power anything for all n. Whatever power n you take, whatever integer power you take, this we already know. Identity element power n, that is always identity element for all n. So definitely E power 4 is equal to E. If E power 4 is equal to E, then can I say E belongs to H? Then can I say E belongs to H? Tell me. E power 4 is E. So can I say E belongs to H? Yes, of course. So this is done. Okay. So identity element belongs to H. So which option is gone? Which option is gone? See, option B is saying H is not a subgroup of G because the identity element is not there. So this statement is a false. I can say this statement is false. Option B is false. Okay, very simple. This is the one thing. Now let's see the next thing. So we have seen identity element is there. Now what about the closure property? What can you say about the closure property? Means the second in this closure property. What can you say about closure property? So can I say is H closed? Tell me, is H closed? What it means? We need to check if A comma B belongs to H, then can I say AB belongs to H? Then can I say AB belongs to H? Tell me. If A comma B belongs to H, then can I say AB belongs to H? Very simple thing I am asking. I am asking that if A comma B belongs to H. So let's assume A comma B belongs to H. What it means? First of all, you tell me what it means. And one more thing. Let's assume AB belongs to H. Then how can you prove that AB belongs to H? See, A comma B belonging to H. A comma B belong to H. How can you prove? How can you prove that AB belongs to H? How can you prove? How can you prove? Very simple. You have to prove that AB power 4 is equal to E. This is what you need to prove. Yes or no? This is what we need to prove. Okay, agree? Is this point clear? See, A comma B belonging to H. How can you say that AB belongs to H? How can you say that AB belongs to H? Okay, this AB means A star B. How can you say A star B belongs to H? Very simple. You need to prove that AB power 4 is equal to identity element. This is what you need to prove. So let's prove it. So if A comma B belonging to H, then from this what you can say? If some element is there in this H, then it means the power 4 is identity element. Okay, A belongs to H. Remember, A belongs to H. So that automatically means that power 4 is identity element. Similarly, B belongs to H. That automatically means that power 4 is equal to identity element. Okay, now let's check what is AB power 4. Now check what is AB power 4. What is that? So what that will be? That will be AB, 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 AB. Agree? That will be AB, 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 AB. Now you tell me, what should I do next? Remember, this is abelian group. The group is abelian. So if the group is abelian, can I write it like this? A, B, 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 B. Can I write like this? Because remember, your group is abelian. You have abelian group. So you can see that this G, this was abelian. Okay, abelian means that for all A comma B, I can say that AB is equal to BA. Okay, for all A comma B, I can say that AB is equal to BA. So you can easily notice that if you have AB power 4, that means AB, 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 AB. Okay, I can use this abelian, I can use this commutative property. Okay, I can use this commutative property and I can write it like this: AA, BB, AB, AB. See what I'm doing? I am writing this like this. So using commutative property, I'm using the commutative property. Using commutative property. Very simple. Now, similarly, what I can do, I can write like this. Okay. Now, similarly, what you can do, basically, you can just keep swapping. You can keep swapping. Just keep swapping. If you keep swapping, then this also you can swap. Then, okay, you just keep swapping. You will ultimately, you will get A, B, 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 B. This is what you can get ultimately, because you can keep swapping. This A, this BA, you can write it AB. This you can write it AB. Then this BA you can write AB. So like this, if you keep swapping, then what will happen? Let me tell you what will happen. See, this BA also you can swap. So what will happen? AAB, AB, BAB. So this also you can swap. You can see. This also you can swap. Okay. Next you can swap this one. Next you can swap this one. Okay. In the next step, you can swap this one. So you can do like this: AA, B, 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 A, B, and so on. If you do like this, if you keep doing like this, then ultimately you will get A, B, 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 B. Now you tell me, this is your A power 4, this is your B power 4. Okay, what are these? See, this is your A power 4, this is A power 4, and this is B power 4. Already we know A power 4 is equal to E and B power 4 is equal to E. So ultimately what you got? Ultimately you got E. Okay, ultimately you got E. So can I say AB power 4 is E? AB power 4 is E. So can I say closure property is satisfied? So what we have done? Remember what we have done? Means we have done this. For all A comma B belonging to H, we have proven that AB power 4 is equal to identity element. Okay. And that automatically means AB belongs to H. So we have proven that closure property is satisfied. We have proven closure property is satisfied. It simply means closure property is satisfied. H is closed. H is closed. So simple. So this is your answer. Okay. So closure property is also satisfied. Which option is gone? If closure property is satisfied, remember H is not a subgroup. This option C is saying H is not a subgroup because it does not satisfy closure property. This statement is also false. This statement is also false. Now all we have to do, just check the inverse property. This is the last property we need to check. So let's check the inverse property. Third one means inverse property. This is what we need to check. So let's check. Inverse property. Let's check inverse property. Is H inverse? Means I can say if A belongs to H, then can I say A inverse also belongs to H? This is what you need to check, right? If A belongs to H, then can I say A inverse also belongs to H? Means I want to check, is H does H have inverse property? Okay, does H have inverse property? This is what I want to check. I want to check, does H have inverse property? Inverse property. Okay, so very simple. Means if A belongs to H, then can I say A inverse also belongs to H? So tell me, let A belongs to H. What I want to prove ultimately, if I want to show the inverse property, then what I need to do? From here, where should I go? Okay, if I want to prove that A inverse belongs to H, then what I need to do? If I want to prove this, then what I need to do? I need to prove this A inverse power 4 is equal to identity element. This is what I need to do. Agree? I need to show this. I need to show that A inverse power 4 is identity element. Then I can say that A inverse belongs to H. This is what I need to show. Okay, so let's show it. So you can see, if A belongs to H, then it automatically means that A power 4 is equal to E. A power 4, that is equal to identity element. Okay, now now you just check this. What is A power minus 4? Means I can say, what is A power minus 4? What is that? Because you know that A inverse power 4. Okay, what is that? Okay, what is A inverse power 4? See, A inverse power 4, that is equal to A power minus 4, that is equal to A power 4 minus 1. Already A power 4 is E. Already A power 4 is E. E power minus 1. What is E inverse? Tell me, what is E inverse? That is E. What is E inverse? That is E. So very simple. So that's it. So what we have done? Tell me what we have done. So remember, this is what we have proven. So if A belongs to, means this is what we have proven, that for all A belonging to H, we have proven that A power minus A inverse power 4 is equal to identity element. And that automatically means A inverse belongs to H. And that automatically means inverse property. Inverse property. So inverse property is also satisfied. So remember, this H, I can say this H is a subgroup of G. Please tell me, did you understand this? The complete explanation, did you understand? The complete explanation, is this clear? Crystal clear? Let me know. Crystal clear? Okay. So in a very detailed way, I have told you every point in a very detailed way, very step by step, I have told you. Okay. Step by step, every point I'm telling you what is happening. So finally, I can say H is a subgroup of G. So simple, very simple. Okay. So what is the answer for this question? The answer will be H is subgroup of G. So the answer is going to be A. For this question, the answer will be A. Okay. So this is a type of question. In the GATE exam, they can ask you this type of question. They can give you some subset. Okay. So G is a group. They can give you some subset and they can ask you, is this subgroup? So this type of question also they can ask you in the GATE exam. Okay. This question has not come in the GATE exam so far. In the GATE exam, so far, this type of question has not come. but definitely they can ask you this type of question, because this is a very standard simple question, right? Agree with me? For this question, do you need any concept other than what we have seen in our lectures? All the concepts that we have seen in our lectures, you just need to use those concepts. Okay, so nothing else is needed. If you want to solve this question, all the concepts that we have seen in our class, in our lectures, only those concepts you need. So this is a simple question. This type of questions can come in the GATE exam. Now let's move on. Now let's see this question. This is a very interesting question. So let's see. The question is asking, for which of the following partially filled Kelly tables it is impossible to complete to make a group? Okay, see, very interesting question, right? Some Kelly tables are given to you. This is partially complete Kelly table. This is also partially complete Kelly table. Some entries are missing. Now the question is asking, it is impossible to complete, to make a group. Means you can never make it a group. You can never convert it into a group. You can never make it a group. You can never make it a group. The question is asking, for which of them it is impossible to make them a group. Okay, very interesting question. And this is a standard question, let me tell you. From a standard resource, I have taken this question. Very interesting question. So let's see the first. So the question is asking, it is impossible to make them a group. So what we will try to do? If the question is asking it is impossible, then what we will try to do? We will try to create a group. Agree? Agree or not? See, very simple. The question is asking, for which of the following partially complete Kelly table it is impossible to make it a group. So what we will try to do? We will try to make a group. If we cannot make a group, then we can say it is impossible. Okay, so let's see the first one. Okay, so tell me, in this first one, you tell me one thing. You need identity element. Do you agree with me? You need identity element. Okay, so let's try to make it a group. Okay, let's try to make it a group. Very simple strategy. So let's try to make it a group. So what I will do, what will be my first step? I need an identity element. We need identity element in a group. You already know this. If you have a group G, star, then these are the things you need. One thing you need is identity element. There must be identity element. Okay, means in the Kelly table, what should happen? There must be some element whose row is same as the header. Okay, there must be some element whose row is same as the header. Means this header is same as this row. They must be same. Okay, similarly, I can say that this column must be same as this column. This column must be same as this vertical header, I can say. Okay, so they must be same. So very simple. You need identity element. So tell me, is it possible B can be identity element? Is it possible B can be identity element? No. Okay, because if B is identity element, then this row must be same as this header. So B cannot be identity element. Is it possible C can be identity element? Is it possible C can be identity element? No, because if C is identity element, then this row must be same as this header, but they are different. They are already different. Next, is it possible D can be identity element? Again, no, because if D is identity element, then this header must be same as this row, but they are already different. Here you have A, here you have C. So what is possible? Which identity element is possible? So the only identity element possible is A. Agree? So A must be the identity element, right? You agree with me that A must be the identity element. A must be the identity element. Okay, so if A is the identity element, then I will do like this: A, B, C, D. I will do like this: A, B, C, D. Okay, is this point clear? Let me know. Now what? Now can you notice? So A is the identity element. Remember, A is the identity element. Now what? What is the next step? Now you can easily notice that, yes, if A is the identity element, then this column must be same as this column. Remember, this column must be same as this, but they are different. Agree? See, very simple. If A is identity element, then this must be same as this. They must be same, but they are different. You can easily notice, but they are different. It means A is not identity element. See, A must be identity element and A is not identity element. There is a contradiction or not? A must be identity element, but A cannot be identity element. A cannot be identity element because here you have A, B, D, C, and here you have A, B, C, D. So definitely I can say this can never be a group. Impossible. This is impossible to be a group. This is impossible to be a group. To be a group. It is impossible to make it a group. Is this point clear? Please tell me. Very simple question and very nice question. This is impossible to convert this into a group. Next, what is the answer for the next? What is the answer for this one? Okay, so tell me here. So in this question also, the same thing. Now you tell me in this question, is it possible C can be identity element? Is it possible C can be identity element? C. Is it possible C can be identity element? Is it possible C can be identity element? Why no? If C is identity element, then I need ABCD here. See, if C is identity element, then this row must be same as this header. So I need ABCD here. Now what is the problem? Now here this is the problem. Now here this is the problem. Here this is the problem. So I can say C is definitely not identity element. Okay, what about the next? Can I say D is the identity element? Can I say D is the identity element? The same thing will happen. If D is the identity element, then ABCD. If D is the identity element, then this header will be same as this row. But again, there is a problem. Again, there is a problem. So what I can say, D is also not identity element. Okay, D is also not identity. Can you notice the same thing will happen for A? Can I say A is identity element? Can I say A is identity element? If A is identity element, then you need ABCD. If A is identity element, then you need ABCD. But again, there is a problem. So A is also not identity element. Okay, A is also not identity element. Okay, finally, can I say B is identity element? If B is identity element, then this must be same as this header. So I can say if B is identity element, then you must have ABCD. Again, there is a problem. In this column, you have repetition. In this first column, you have repetition. In a group, you cannot have repetition in any column, any row. If you have a group, then in any row, in any column, you cannot have repetition or in the Kelly table. So very simple, B also cannot be identity element. So tell me, no element is identity element. So again, what I can say, impossible to create a group, right? Agree? Again, impossible to make a group. It is impossible to make a group. Very simple. So the question is asking for which it is impossible. So I can say for A it is impossible and for B it is impossible. So for these two it is impossible. Here also impossible. Next, let's see the next part. So tell me here, what about this one? Can you notice the same problem will come? Can I make A identity element? Okay, so first of all, let's see. Can I make B identity element? Is it possible B can be identity element? No, right? B is not identity element. Definitely B is not identity element. Okay, because you can notice already these are different. So B cannot be identity element. What about this one? Can I say C is identity element? Can I say C is identity element? Again, they are different. So C is also not identity element. Okay, what about the next? Can I say D is identity element? Is it possible D can be identity element? Is it possible? Please tell me. Is it possible D can be identity element? See, if D is identity element, then this row must be same as this header. So if D is identity element, then you must have ABCD, but there is a problem. Now you have repetition in this column. In this first column, you have repetition. But I told you, in the Kelly table of a group, in any row, in any column, you cannot have repetition. Okay, very simple. In any row, in any column, you cannot have repetition. Okay, in a Kelly table of group. So you can see this D also cannot be identity element. Very simple. D is also not identity element. What about finally? What about A? Okay, so let's see. Can I make A as identity element? Let's see. Okay, let's see. Can I make it identity element? So if A is identity element, the only possibility is A is identity element. This is the only possibility that A is the identity element. Now you can notice if A is the identity element, then I must have this. Okay, now is there any problem? Now let's check. Is there any problem? So now let's fill this. Can I fill it? So remember, A is the identity element. This is the only possibility, that A is the identity element. Okay. Now you tell me, what can I write here? See, already B comma C is there. So A comma D is remaining. A comma D is remaining. So can I put D here? No, I cannot put D because this will be a problem. So I can put D comma A like this. I can put D here. I can put A here. Okay, very simple. Now, can you notice? Can you notice what is the B inverse? Now tell me, what is the B inverse from here? What is the B inverse? A is the identity element. So B inverse is D. So B inverse is D. So can I say if B inverse is D, then automatically D inverse will be B? Then automatically D inverse will be B. So it means here you must have A. Here you must have A. Okay, very simple. Now what about the next? Now what can I write here? I need to write D here. Agree? I need to write D here. Okay. So far it is okay. I need to write D here. Now what should I write here? Tell me, what should I write here? I should write A. I should write A, and there is a problem. So I cannot go further. Yes or no? I cannot go further. Again, this is impossible. Again, this is impossible. So here again, you got impossible. You cannot move further. Again, you got impossible. Is this point clear? You cannot fill this entry. This entry you cannot fill. You cannot fill this entry. Very simple. Again, this is impossible. So this is also impossible to create a group. Okay, so for this also I can say impossible to create a group. Impossible to create group. Okay, what about the next? What about this one? Here you can notice A is not identity element. Already you can see. You can see A is not identity element. You can see B is not identity element. You can see B is not identity element. You can see C is not identity element. You can see C is not identity element. So the only possibility, what is that? So the only possibility, what is that? That is D is the identity element. The only possibility is D is the identity element. Okay, D is the identity element. This is the only possibility. Now you tell me. Okay, now you tell me, what should I write here and here? What should I write here and here? The only possibility is that D is the identity element. Okay, now you tell me, what should I write here? So already B comma A is there. So C comma D is remaining. C comma D is remaining. I cannot put C here. So I need to put D here. I need to put D here. So I need to put C here. Okay, see, there is a problem. Can you notice there is a problem? I cannot put C here. I cannot put C here. And I cannot put C here also. Okay, so there is a problem. See, I cannot put C here also. Because of this, I cannot put C. I cannot put C. Definitely, this is, I can say, not C. And because of this, I can say this is also not C. So again, can you notice? Again, can you notice? I cannot fill these entries. Okay, here also I cannot put C because of this. And here also I cannot put C because of this. So again, this is impossible. Agree? Is this point clear? Again, this is impossible. So very simple. I can say that option A, option B, option C. What is the final answer? What is the final answer? Tell me. The final answer is option A, option B, option C, option D. For all of them, it is impossible to create a group. Impossible to make a group. Did you find this question interesting? Please tell me. This is a new type of question. In the GATE exam so far, this type of question has not come. But this is a standard question. This question is taken from standard university, top university. So you can see this type of questions can come in the GATE exam. Okay. So very interesting. Is there anyone here who did it correct in the quiz? During the quiz, did you get these 2 marks? Did you do this correctly? Anyone? Okay, let's move on. So let's see this one. The question number 15. Okay, let's see. This is quite simple. What is this group? If G is a group, then the definition of subgroup generated by G is given to you. Okay, G is a group. Okay, and this small g is the element. Now, subgroup generated by small g, that is given to you. This we already know. Agree? Okay, this we have already seen in our class, in our lectures. This we already know. This we already know. Some information is given to you which we already know. The definition is given to you. Subgroup generated by G. This definition is given to you, and this we have already seen in the lectures. So this we already know. Next, this also we know. This is our UN group. Multiplication modulo n group. This also we already know. Okay, this is the UN group. Multiplication modulo n, unit group. This is our unit group. UN. You already know what is UN. What is UN? Tell me. UN. This is basically unit group. Unit group of Zn. Unit group of Zn. Okay. So this we have already seen. If you remember, I told you that in this UN, basically you have those elements from 1 to n minus 1. Okay. You have those elements from 1 to n minus 1. From 1 to n minus 1, you have those elements which are relatively prime to n. Okay, which are relatively prime to n. X GCD of x comma GCD of x comma n is equal to 1. Means I can say I can say x comma n are co-prime. Are co-prime. Okay, so this is your unit group, if you remember. Okay, we have already seen this. So this is the unit group. Now, this unit group under multiplication modulo n, this is a abelian group. Okay, this is always a abelian group, correct? This is always a abelian group. This also we have seen. We have seen everything about this unit group. This UN, this is the unit group of Zn. Okay, you can call it UN. See, this UN, there are many different names for it. You can call it unit group of Zn. This is what you can call it. Or what you can call it, you can simply call it UN, or you can simply call it multiplication modulo n group. You can call it multiplication modulo n group. Okay, so many different names are there. You can call it. Okay, very simple. Because this UN under this operation multiplication modulo n, this is a abelian group. We already know. Okay, so definitely this is abelian group. You don't even have to check it, right? The option B, you don't even have to check. This is abelian group. Agree? Option B, you don't have to check because this will be always abelian group. Okay, UN, that is always abelian group. So you don't even have to check. Now let's see the remaining options. Now the question is asking for U24. Okay, so first of all, what is U24? So tell me, what is U24? Means in this U24, what are the values? You can see 1 is co-prime to 24. Next, 2 is not co-prime to 24. Next, I can say 3 is not co-prime. 4 is not co-prime. Next, 5 is co-prime. Next, I can say 7. After that, what is the next value? The next value will be 11, 13, 17, 19, and 23, right? Yes or no? Is this point clear? This is your U24 because these are the values. Remember, these are the values which are co-prime to 24. Okay, for all of them, you can see these are co-prime to 24. Or I can say for all of them, I can say that GCD of 24 comma these. 24 comma these. Okay, let's call them X. So 24 comma these, this will be 1. So very simple. Now you tell me in this is the U24. You tell me here, what is the subgroup generated by 1? This 1 is the identity element, right? This is the identity element for multiplication. So this 1 is the identity element. So what is the subgroup generated by 1? Tell me. What is a subgroup generated by 1? Generated by 1. Remember, 1 is the identity element. Subgroup generated by 1. So what that will be? So I told you that identity element can only generate itself. Identity element can only generate subgroup generated by 1. What is the subgroup generated by 5? What is the subgroup generated by 5? How do you find? Very simple. 5 power 1, that is 5. What is 5 power 2? Tell me, what is 5 power 2? Take your calculator. What is 5 power 2? 5 5 power 2 means 5 multiplied by 5. See, that will be 5 multiplied by 5 mod 24. So that will be also 1. That also will be 1, right? So 5 power 2 is 1. So can I stop here? You got identity element. So can I stop? Yes, I can stop. Agree? I can stop. See, very simple point that now I can stop, because if you see subgroup generated by 5, this is the definition of subgroup generated by 5. That will be 5 power n, where n is integer. This is the definition. This is the definition of subgroup generated by 5. Now you already know that 5 power 1 is 5. 5 power 2 is equal to identity element. That is equal to identity element. Okay, what it tells you, what is the inverse of 5 from here? From here, what you can say? What is the inverse of 5? 5 inverse is 5, because 5 star 5 is equal to identity element. Okay, 5 star 5 is equal to identity element. So it automatically means that 5 inverse is equal to 5. Okay, very simple. So 5 inverse is 5. Now you tell me, what is 5 power 3? What is 5 power 3? Remember, 5 power 3 means 5 power 2, 5, and this is already identity element. So ultimately you will get 5. So 5 power 3 will be 5, and that you already have. That you already have. Next, what will be 5 power 4? That will be identity element. What will be 5 power 5? That will be 5. Okay. So what will be 5 power 6? That will be identity element. 5 power 7 will be 5, and so on, right? And so on. What is 5 inverse? Let's go in the negative direction. Let's go in the negative direction. What is 5 inverse? That is also 5. That is also 5. That we already have. What is 5 power minus 2? That will be identity element, and so on. So can you notice what 5 can generate? Tell me what 5 can generate. Can you notice? Can you notice what 5 can generate? 5 can only generate these two. 5 can generate 5, and 5 can generate identity element. See, 5 can generate 5. Also, 5 can generate identity element. So 5 can generate only 2 elements. Is this point clear? Is this point clear that 5 can generate only 2 elements? Whatever you do, 5 can generate only 1,5. So can I say 5 is the generator? Can I say 5 is the generator? See, 5 cannot generate the entire group. I can say 5 cannot generate the entire group. 5 cannot generate all the elements. 5 cannot generate all elements of U24. 5 cannot generate all elements of U24. So that is the reason I can say 5 is not a generator. For 5, I can say that this is definitely not a generator, because 5 cannot generate all the elements of U24. In the U24, how many elements are there? In the U24, total 8 elements are there. I can say the order of U24, that is actually equal to 8. Total 8 elements are there. Okay, but you can see 5 cannot generate all the elements. 5 can only generate 1,5. Okay, what about the next? What about 7? What about 7? So 7 can generate 7. Next, what is 7 power 2? What is 7 power 2? See, 7 power 2 means, that means 7 multiplied by 7 mod 24. Because the operation is multiplication modulo 24. You know the operation. You already know the operation. The operation is multiplication modulo 24. Multiplication modulo 24. So I can say this will be, again that will be 1. Again that is going to be 1. That is identity element. Can I stop? Can I stop? Can I stop? Yes, I can stop. You got identity element, so you can stop. So 7 can generate only 2 elements. Remember, 7 can generate only 2 elements, that is 1,7. So 7 is also not a generator. What about the next? What can I say about 11? What can I say what 11 will generate? See, 11 can generate 11. 11 can generate what? What is 11 power 2? Can you check? 11 power 2. That means 11 multiplied by 24. Anyone want to tell me what is this value? Can you check? 11 multiplied by 11 mod 24. What is this value? Is this value 1? Please tell me. Is this value 1? Let me know. See, let me check. So yes, this value will be 1. Okay, you can check. You can check this. This value will be 1. So can I stop? You got identity element. This is your identity element. So you can stop. So you can stop. So what 11 can generate? 11 can generate 1 comma 11. 11 can generate 1 comma 11. So 11 is also not a generator. What about the next one? What about 13? What 13 can generate? See, 13 can generate 13 power 1. That is 13. What is 13 power 2? What is 13 power 2? See, let's check. 13 power 2 means 13 multiplied by 13 mod 24. What is this value? Tell me. This value is also 1. Okay, you can check. This value is also 1. So this value is also 1. So very simple. So I can say what 13 can generate? The subgroup generated by 13. The subgroup generated by 13, that is also 1 comma 13. So 13 is also not a generator because 13 cannot generate all the elements. Okay, what about the next? What about the remaining? What can you say about 17? What 17 can generate? See, 17 power 1 is 17. What is 17 power 2? Can you check? Can you check? What is 17 power 2? Okay, let's check. You can use the calculator. In the GATE exam, there is calculator. So you can use the calculator. Tell me. So that also will be 1. Okay, that is also 1. So you can see that is also identity element. Okay, very simple. Again, I can say that 17. What 17 can generate? It can generate 1 comma 17. So I can say this is also not a generator. So 17 is also not a generator because it cannot generate all the elements. It cannot generate all the elements. What about the next? 19 comma 30, 23. What can you say about 19? 19 will generate 19 power 1, that is 19. What is 19 power 2? What is 19 power 2? What is 19 power 2? You can check, that also will be 1. You can check. And what is 23? See, what is 23 power 1? That is 23. And what is 23 power 2? That also will be 1. So can you notice something very interesting? That there is no generator here. Okay. In this group, can you notice in this group, what we have seen? In this group, we have seen that 1 inverse is 1. Actually, every element is inverse of itself. In this group, you can notice for every element, I can say that it is inverse of itself. Every element is inverse of itself. Okay, every element means 5 inverse is 5, 7 inverse is 7, 11 inverse is 11, 13 inverse is 13, 17 inverse is 17, 19 inverse is 19, and 23 inverse is 23. So very simple. Okay. So this is the point. And you can notice that no element can generate all the elements. Agree? In this, there is no generator. There is no generator. There is no generator. There is no element which can generate all the elements. So I can say that U24 is not cyclic group. Okay, this is not a cyclic. This group is not cyclic. This group is not cyclic. Okay, very simple. I hope all these points are clear. Okay, so remember this point, one point. If you have a group, then this notation, what this notation means? What this notation means? This notation means subgroup generated by A. This means subgroup means generated by A. Means what are the elements? Subgroup generated by A. Okay, this is subgroup generated by A. This symbol means a subgroup generated by A. And this means all the elements which A can generate. Okay, A power n, where n is integer. Integer powers of A. So all the elements which A can generate. So this means all the elements A can generate. Set of elements A can generate. Set of elements that A can generate. Okay, A can generate. Set of elements that A can generate. Now you tell me one more thing. Now you tell me one more thing. Here, the cardinality of this set, what is that? Means the cardinality of this set, what that will be? Tell me. The cardinality of subgroup generated by A means how many elements A can generate. That is same as number of elements A can generate. Number of elements A can generate. That is same as number of elements A can generate. And that is same as the order of A. That is same as the order of A. We have already seen all these things in our lectures. In our lectures, all these things we have seen. Okay, all these things. I told you that if you want to find order of A, you have a group and you want to find order of A. Let's assume A is element. You want to find order of A. Then there are two definitions. What is the definition one? What you can do? The definition one is that you can find the subgroup generated by A and the cardinality of this. So I can say the order of A, that will be equal to cardinality of subgroup generated by A. Subgroup generated by A. Correct? Subgroup generated by A. This is definition one. What is the another definition? The another definition is smallest positive integer. The another definition is smallest positive integer n, such that A power n is equal to identity element. Okay, such that this happens. So you can apply any of these definitions. Is this point clear? All these concepts we have seen in our class. In our lectures, we have seen all these concepts. Means what is this? We have already seen. What is the order of an element? So this is just a revision of all those concepts. Very simple. Now let's come to this question. What is the answer for this question? So in U24, the size of subgroup generated by 13 is 2. Yes, that is correct. That is correct, right? The size of subgroup means this is the subgroup generated by 13. This is the subgroup generated by 13. So the size is 2. This is the subgroup generated by 13. 13 can generate this. So the size is 2. The size of subgroup generated by 13, that is 2. Yes, that is correct. This is cyclic group. This is not cyclic group. The order of element is equal to the size of subgroup generated. Is this correct? Is this correct? The order of element is equal to the size of subgroup generated by Y. Yes, we have already seen this in our class, in our lectures. Okay, these are the two definitions of order of element. Very simple. Order of element is equal to size of subgroup generated by Y. Okay, so anyway, so finally for this question, the question is asking for true. So what is the answer? The question is asking for true. Answer will be ABD. ABD will be the answer. Let's move on. Let's see this question. This is very interesting question. Okay, so let's see this. G is a group. A comma B belonging to G means A comma B. These are elements of G. The question is asking which of the following statements are true. Okay, so first to tell me about option D. In any group, there is exactly one element of order 1. Is that correct? In any group, there is exactly one element of order 1. Yes, that is true. Because in any group, remember, this we already know that option D is true. Why? Because if you take any group, G comma star, if you take any group, you can take any group you want. Okay, so in this group, what will happen? Two things will happen. First of all, that the order of identity element. For identity element, what will happen? For identity element E, what will happen? The order of identity element will be 1. Okay, order of identity element will be 1. The second point, for all A which are not identity element, for all A other than identity element, okay, for all A other than identity element, the order of A, that will be greater than or equal to 2. That will be greater than or equal to 2. Very simple. Okay, at least 2. So these points actually in our lectures we have seen. So there is nothing here. We have already seen. Actually, if you notice, this D is true. Why this D is true? Because if you see in any group, you take any group G you take. Now what will happen? For identity element, what will be how many elements identity element can generate? Tell me, how many elements identity element can generate? How many elements identity element can generate? Only one. Only one. Okay, only one. So that is the reason I can say that order of E. That is the reason I can say order of E is 1, because E can generate only one element, that is itself. Identity element can generate only identity element. So I can say number of elements generated by E, that is 1. Number of elements generated by identity element, that is 1. But you notice one thing. For all A which are not identity element, for all A which are not identity element, you tell me at least how many elements will be generated? You tell me, at least how many elements will be generated? At least. See, at least 2 elements will be generated, because A power 1 will be A power 1 will be A, okay, and so on. So you can see at least at least 2 elements will be generated. At least two, because A power 1 will be A, and there will be some more elements will be generated. Okay, very simple. I hope this point is clear. You can stop when you generate identity element. You can stop. Where can you stop? You can stop when you generate identity element. Okay, very simple. So you can very easily see that identity element can generate only itself. Identity element can generate only one element. But all the remaining elements, for all A which are not identity element, at least 2 elements will be generated. At least 2 elements will be generated. So this is the simple point. So I can say that in any group, there is exactly one element of order 1. Yes, that is correct. Okay. What about the next one? What about option? What about option A? The order of A is same as order of A inverse. This we have seen in the class. In our lectures, we have seen the order of A is same as A inverse. What is the reason? Do you remember the reason? Do you remember the reason? What is the reason for option A? Option A is true. Means order of A that is same as order of A inverse. Okay. And the reason I told you, because you can notice the subgroup generated by A, that is also A power integers. Yes or no? This is also A power integers. And that is same as subgroup generated by A inverse. Okay. So A comma A inverse, they will generate the same subgroup. Agree? I told you that subgroup generated by A. What is that? See, subgroup generated by A. That means A power 0, A power plus minus 1, A power plus minus 2, and so on. Similarly, subgroup generated by A inverse. What that will be? Subgroup generated by A inverse. What that will be? That also will be same. See, anything power 0, that will be E. So here also A inverse power 0, that will be actually E. That will be actually E. See, this will be actually E. Other than that, again, you will have A power plus minus 1, A power plus minus 2. So can you notice they are same? I hope this point is clear. See, very simple point, that A comma A inverse, they will generate the same subgroup. You have any group you take, if A belongs to G, then you can notice the subgroup generated by A, that is also integer powers of A. That is also integer powers of A. And subgroup generated by A inverse, that is also integer powers of A. So that is the reason I can say order of A. You can easily see that order of A, that will be same as order of A inverse. Order of A will always be same as order of A inverse. So this is a statement. So I can say this we have seen actually in our lectures. This question is from the class. So I can say option A is correct. Okay. Now we need to see the remaining. What about this one? Option B comma option C. These we need to see. Option B comma option C. So before you see option B comma option C, tell me the answer here. Tell me the answer for this question. Before we see option B, option C. In a group, if A power n is identity element, then can I say what is the order of A? In the part 1 also we have seen this. If A power n is the identity element, then order of A definitely will be less than equal to n. This we have seen in the part A also. Okay. Very simple. Because order of A means that is smallest integer. That is smallest positive integer. That is smallest positive integer. So m, such that A power m is equal to identity element. So remember this word smallest. Don't forget about this word smallest. Smallest positive integer such that A power m is equal to E. So I can say if a power n is equal to identity element, then definitely I can say that this smallest value will be less than equal to n. Okay, the smallest value. If a power n is equal to identity element, then the smallest value will be less than equal to n. So this is correct. Option D is correct. Okay. Do you remember I told you this something I told you in the last in the part I can say part 1 in the previous part. Okay. So do you remember that how to prove that order of if you have a group, then how to prove order of x equal to order of y? How to prove? Tell me how to prove that order of x equal to order of y? That order of x equal to order of y. How to prove that? How to prove this? Tell me. Do you remember? This we have seen in the part A. How to prove order of x equal to order of y? I told you that two things you need to prove. You need to prove two things, that if x power n is equal to identity element, then show that y power n is equal to identity element, and if y power n is equal to identity element, then show that x power n is identity element. These two things you need to do. Okay, if you remember, this we have seen in the part A, in the part 1. So I can say that if you want to prove that order of x equal to order of y, if you want to prove this, then you need to do two things. Okay, if x power n is identity element, then y power n should be identity element. If y power n is identity element, then x power n should be identity element. This is what you need to do. Okay, so let's start. So let's see the option. First, let's see option B, option C. Let's see this. Let's see option C. Order of AB. Order of AB. That is same as order of BA. Okay, let's try to prove it. Take your copy pen. Take your copy pen. What we need to prove? What we need to prove? We need to prove that order of AB. That order of AB. That is same as order of BA. Okay. Order of AB is same as order of BA. This is what you need to prove. So let's see the first side. What is that? Means if AB power n. Okay, remember this is your x and this is your y. So I can say if AB power n, then can I say that BA power n will be E? Sorry, if AB power n is E, then can I say BA power n will be equal to E? Okay, let's check this. Can I say this? Okay, this is what I'm asking, that if this happens, if AB power n is E, then can I say that BA power n will be E? So let's check. So this is the one thing, that AB power n is equal to E. Okay, what it means? It means AB total how many times? N times. That will be equal to E. Okay, that will be equal to E. Now remember, if it is like, for example, if it is 5 times, if it is 5 times, then what I can write it? I can write it, see, your BA, you are getting BA. So I can write it A, BA power 4, B equal to E. Agree? Agree or not? Means if it is 5 times, for example, if AB power 5 is equal to identity element, if this happens, then what I can say? Then I can say that I can write it like this. A, BA power 4, B equal to E. So here also the same thing I can say. I can write it A, BA, and so on. BA. Okay, so I can say it will be B power n minus 1, B is equal to identity element. Okay, is this point clear? So very simple. So if this happens, then we can say that this will happen. Now you find what is BA power n. Now find what is BA power n. Now, okay, now what you do? Now find what is a BA power n. What will be BA power n? So let's see this. So tell me what will be BA power n? Now you check what is BA power n. BA power n. That means BA, and so on, BA. What is that? So here you can see, I can write it BA power n minus 1, BA. Agree? I can write it BA power n minus 1, BA. This is what I can write it. Okay. Now you tell me what is this? Now you tell me what is this one? BA power n minus 1 B. What is this one? From here, what you can say? From here, what you can say? What is BA power n minus 1 B? What is that? Tell me. That will be A inverse. That will be A inverse. So you can see this is a inverse. So ultimately what I got A inverse A, that is equal to identity element. So what we have proven? Tell me what we have proven. So what we have proven, let me know. We have proven, this is what we have proven. We have proven that if AB power n is identity element, then definitely what will happen? That BA power n will also be identity element. In the same way, can you prove the other direction? In the same way, can you prove the other direction? Means now can you prove this? Tell me. Now can you prove the second side? Means if BA power n, if that is equal to identity element, then can I say AB power n will be identity element? The same way, can you prove it? Take your copy pen, do it. See, very simple. The same way can I prove it, that if okay, means a BA power n is E. So what I can write it? Okay, what I can write it? I can write it BA, and so on. BA. Okay, next you can see, I can write it. Okay, I can write it like this. I can write it AB power n minus 1 A. That is equal to identity element. This is what you can write. Okay, this is what you can write. Right? Correct? This is what you can do. Next, from here, now you find, now what you do? Now you find AB power n. But from here you can notice one thing. That what is AB power n minus 1 A? What is that? Tell me. What is that? Means this AB power n minus 1 A. What is this? This is equal to B inverse. So that is equal to B inverse. So now you find, okay, now what you do? Now you find AB power n. Now find AB power n. Now you find AB power n. So what that will be? See, AB power n, I can write like this. AB power n minus 1 AB. Okay, and this you already know. What is this one? AB power n minus 1 A. AB power n minus 1 A. That is equal to B inverse. So it will be like B inverse B. That is equal to identity element. So what we have proven? That's it. So hence we have proved this. Hence proved. Agree? Hence proved. Please tell me, did you like this proof? The similar proof we have seen in the last lecture also. If you remember, see, we have seen this similar proof in the last lecture also. If you remember, in the last class we have already seen. So these two things we have done. The same question we have seen, basically the similar question we have seen in the part 1 also. If you remember, there was something like, what was that question? Order of BAB, that is equal to order of ABB, something like this. Do you remember? This was the question or not? Do you remember the question from the part 1? And order of AB is equal to order of BA. So these things we have done. These things we have proven. In the same way. Proven in same way. So are you confident now? That in the exam, if they give you this type of option, can you handle it? Now, are you confident that, okay, this type of question can you solve? Are you confident? If they give you this type of question, are you confident? See, if I ask you in the exam, if they give you this type of question, that order of something, okay, order of, for example, alpha, that is equal to order of beta. Okay, so if you want to prove this, then can you do this? Tell me. Can you prove it? Can you prove this type of question? This type of questions. Okay, is this point clear? See, very simple. I am saying that these two questions we have seen. In the part 1, we have seen this question in the part 1, and in the part 2, we have seen this question. So very simple. The part 1 link is in the description. Okay, this video I will put on the YouTube channel, on the Go Classes YouTube channel. So if you want to watch the part 1, then in the part 1 we have done this. That part 1 description, in the description you can find the link. Okay, so link of part 1 you can find in the description. But the point is, these two things we have done. We have proven these two things in the same way. So I'm just asking, are you confident that this type of questions you can do? Please tell me. This type of questions, that order of alpha is equal to order of beta, this type of questions can you do? I hope you can do this type of questions now. So let's move on. So here you can notice that order of AB is equal to order of BA. Now, what about option B? Option B is remaining. Can I say order of A is equal to order of G inverse AG? The same way you will prove. Agree? We will prove in the same way. Now, can you try this? Please try this. The same way we can prove this also. The same way we can prove this also. So let's try this. Can you try this one? So your option B, what is option B? See, option B is saying that, can I say order of A that is equal to order of G A in G A J G inverse. Okay, this is the question, right? Correct? The question is asking this, that order of A is equal to order of G inverse AG. Okay. G inverse AG. So the question is asking, the order of A is equal to G inverse AG. This is what you need to prove. Is this true? So how will you do it? Please tell me. How will you do this question? Again, the same way. The same way. If A power n is a identity element, then can I say this is okay? The same, this question you will solve in the same way. What is the first part? What is the first part? The first part is, if A power n is equal to identity element, then can I say G inverse A G power n will be equal to identity element? Okay. See, first of all, you see what is this? G inverse A G power n. What is this one? Okay, first let's see this. G inverse A G power n. What that will be? Okay, for example, let's see what this power 3 will be. What that will be? Power 3. That power 3 will be like this. G inverse AG, G inverse AG, G inverse AG. Now you can see, what is this? This is identity element. This is an identity element. This is also identity element. So what you got? You got G inverse A power 3 G. Is this point clear? You got G inverse A power 3 G. So now you tell me, if I have power n, then what that will be? Means G inverse A G power n. What that will be? That will be G inverse A power n G. Okay, like this you can do. Very simple. Now you tell me, if A power n is equal to identity element, then what this means? A power n, that is equal to identity element. Okay, so what is G inverse A G power n? What that will be? That will be equal to G inverse A power n G. Now already A power n is identity element, so it will be G inverse G, that is identity element. So yes, so this we have done. Okay, what about the other side? What about the other side? We need to also prove the other side. The second side also we need to prove. We need to prove that if G inverse AG, if this power n is equal to identity element, then prove that A power n is also identity element. Okay, this is also what we need to do. Agree? Yes or no? We need to prove this side also. We need to prove this side also. This side also we need to prove. Means if G inverse AG power n is equal to identity element. So remember, G inverse AG power n, that is identity element. What this means? This means G inverse A power n G is equal to identity element. Now from here, what we need to find? Please tell me what we need to find. We need to find this. From here, we need to find A power n, right? From here, you need to find What is A power n? From here. So remember this G inverse A power n, G is equal to identity element. Now you can multiply both sides with G inverse. Let's multiply with both sides with G inverse. A power n G, G inverse, that is equal to G inverse. That is equal to G inverse. This is same as G inverse. So now this will be identity element. So from here, what you got? You got G inverse A power n is equal to G inverse. Now what you can do? Now you can multiply with G. On both sides, you can multiply with G. Or what you can do? You can simply write it like this. See, you can simply write like this. This same thing you can write like this. G inverse A power n is equal to G inverse identity element. In a group, left cancellation can I do? In a group, can I do left cancellation? In a group, can I do left cancellation? Yes, I can do left cancellation. So you can see this I can cancel with this. So from here I got A power n equal to identity element. Isn't it interesting? Please tell me. Very simple. So this is what we have done. So this is also yes. So what we have done? So 3 questions we have done. This type of questions. Okay, please note this type of questions. What type of questions? Please note. What type of questions we have done? Type of questions. This type of question that you have a group G, and this type of question that prove that order of X is equal to order of Y. Okay, this type of question. Okay, this type of question prove that order of X equal to order of Y. This type of questions we have done. Okay, we have done. Actually, three questions we have done. Actually, 3 questions we have done. This type of questions we have done. Total 3 questions we have done in a complete detailed way. 3 questions in the same way. In the same way you can do them. In the same way. So tell me, are you confident now? After solving 3 questions of this type, order of X equal to order of Y, like order of AB equal to order of BA, order of BAB equal to order of ABB, order of A equal to order of G inverse AB, G inverse AG. So tell me, are you confident now? This type of questions we have done, 3 questions we have done, this type of 3 questions we have done. In the same way we have done all these 3 questions in the same way. Are you confident you can do some new variation? If I give you some new question, can you do? Please tell me. The same way you need to do. Very simple. If X power n is identity element, then prove that Y power n is identity element. Similarly, if Y power n is E, then prove that X power n is E. So in the same way you need to do. Very simple. Nothing. There is nothing here. Okay. So in this question, what will be the answer? All options are correct. A, B, C, D. All the options are correct here. Okay, let's move on. Let's see this question. Actually, this question is not in the GATE syllabus. That is the reason in the question I have written that this is not in the GATE syllabus. You can see structure isomorphism is not part of GATE syllabus. But still, I have given this question just for, I can say, for intuition. So if you don't solve this question, if you don't get correct answer, then don't worry about it because this is not in the GATE syllabus. Okay. So did you try this question? Just give me 1 second. Did you try this? Let me know. Okay. So let's do this. First of all, do you remember I told you that some things I told you in our group theory lectures? In our group theory lectures, we have seen isomorphic, not isomorphic, all those things. Do you remember? We have already seen this. Okay. So I told you, for example, if you remember, order 4, how many non-isomorphic groups are there? Like order 4 groups. If you remember, order 4 groups. I told you how many non-isomorphic. How many templates are there? How many non-isomorphic? How many non-isomorphic? How many non-isomorphic groups? Okay, non-isomorphic groups means how many templates? Okay, non-isomorphic group means basically template. That simply means template. How many template are there? How many template are there? And you know the answer is 2. There are only 2 templates. Okay, that you already know. Now let me tell you. Okay, structure isomorphism. Structure isomorphism. Structure isomorphism. Isomorphism of structure. Structure isomorphism. Structure isomorphism is not in the GATE syllabus, but the question is saying that what is structure isomorphism? Two structures are isomorphic. We will say that two structures are isomorphic if they have exactly the same structure. They have the same behavior, but their elements are different. They have same behavior, but their elements are different. If you remember, for example, can I say these two structures are isomorphic? Like I am giving you. So for example, I can say like 0, 1, 0, 1. Okay, so tell me this. Okay, this structure. First of all, is this a group? This structure. Yes, here you can notice your I can say your base set is 0, 1, and the operation is multiplication. The operation is a multiplication. Is this a group? This is not a group, right? Okay. So this is not a group. Now let me give you like this. Now you tell me. Now you have your structure, your base set is 0, 1. Your base set is 0, 1, and your operation is addition modulo 2. Addition modulo 2. Now you tell me, is this a group? Yes, this is a group. Yes, this is a group. Now you tell me, for order 2, how many groups are there? For order 2, if you have order 2, then how many groups are there? How many groups? How many group templates? How many group templates are there? How many group templates? Only one template. Because see, if you have order 2, then you have only one template. What is that? The template will be like this. There is identity element, there is identity element, there is A. Now, because E is the identity element, so this will happen. Because E is the identity element. And because this is a group, so automatically this will be E. Can you notice? This is the only template possible. Can you notice? Can you notice? This is the only template possible. Now let me ask you. If I create any order 2 group, can I say that will be same as this? That will have same behavior as this. Can I say? If I create any group of order 2, can I say that will have the same behavior as this? That will have same behavior as this. For example, you can notice this has the same behavior as the previous one. You can notice this has the same behavior. You have identity element. This is your identity element. This is your element A. So you can notice this has the same behavior as this. You can easily notice. Okay. So whatever you create, for example, if you want, you can create this also. Like let me give you. For example, 1, minus 1. 1, minus 1 multiplication. Is this a group? 1, minus 1 multiplication. Yes, this is a group. Okay, 1, minus 1. 1, minus 1 multiplication. So here also the same thing will happen. Here also the same thing will happen. Can you notice the same structure? Can you notice they have the same structure? The same structure. This is your identity element. This is your element A. The same structure you are getting. Exactly same structure. Behavior is same. But can you notice names are different? The names are different, but the behavior is same. Agree? Here the identity element is 0. Here the identity element is 1. Here the element A is 1. Here the element A is minus 1. But the behavior is same. Okay. So that is the idea. That is the idea of structure isomorphism. That is the idea of structure isomorphism. Structure isomorphism. Structure isomorphism means the same behavior, but the names are different. Okay, structure isomorphism. Isomorphism means same structure. Same structure, same behavior, same structure, same behavior. Same structure, same behavior, same properties. Same structure, same behavior, same properties. Same properties. But the names are different. Is this point clear? Please tell me. Let me know. Is this point clear? Structure isomorphism means same structure, same behavior, same properties, but the names can be different. The names can be different. For example, here you have 0, 1. Here you have 1, minus 1. But the point is, this is also order 2 group. This is also order 2 group. And this is also order 2 group. This is also order 2 group. they both have the same structure. This is the behavior. This is the order to structure. This is the order to group structure. I hope this point is clear. Okay, very simple. This is the order to group structure. Means, remember, here the names are different. Here 0, 1, here 1, -1. The names are different. But this is also order to group. This is also order to group. So they have the same behavior as this. They have the same behavior as this. Okay, this is the behavior of every order to group. So very simple. Same behavior, same properties, same structure, but the names can be different. The only thing is, I can say names may be different. What is the only thing? That is like names may be different. Names may be different. Names may be different. Everything else is same. Very simple. I hope this point is clear. Okay. So you tell me one thing. You tell me one thing. If you have two structure, simple question I'm asking. Very simple question I'm asking. If you have two structure A, B. Okay. If they are isomorphic, then what you can say? If they are isomorphic, you have two structure A, B. If A is isomorphic to B, okay, this is the symbol for isomorphic. This is the symbol for isomorphic. You tell me one thing. If they are isomorphic, if they are isomorphic, then what you can say? They will have the same properties. Agree with me? Agree with me? Okay. Then what will happen? If they are isomorphic, then what will happen? See, then tell me, they will have the same properties. If they are isomorphic, then they will have same properties. Then A, B have same properties. Same properties. Okay, same properties means, you tell me, if A is group, then definitely B should be a group. Agree with me? Okay, they should have same properties. They should have same properties. So for example, I can say, if A is commutative, then can I say B must be commutative? Tell me. If A is commutative, then can I say B must be commutative? Then can I say B must be commutative? Can I say B must be commutative? Yes, of course, because they have same properties. Ultimately, they have the same behavior, same properties. I hope this point is clear. See, two structures you have A, B. They are isomorphic. If they are isomorphic, then they must have same properties. If A commutative, then B commutative. If A commutative, then B commutative. What is the another property? The another property, for example, I can say that, for example, if I can say like, you can say, if A is group, then B is a group. Agree with me? If A is a group, then B is a group. Like this. I hope these points, I hope these points you are getting. Okay, that they have the same properties. For example, I can say, if A is associative, then B is associative. For example, I can say, if A is associative, then B is associative. If A has identity element, then B has identity element, right? I can say, if A has identity element, okay, if A has identity element, then B has identity element. Ultimately, they have the same properties. If two structures are isomorphic, then they have same properties. Okay, one more thing I want to ask you. If two things are commutative, can I say they are isomorphic? If two things are commutative, can I say isomorphic? They are isomorphic. Tell me, if A, B are commutative, means structure, you have two structures, and if they are commutative, then can I say they are isomorphic? Can one property make you isomorphic? See, very simple. Okay, you and me are isomorphic, so we have same properties. We will have same properties. But okay, can few properties, if we have same, if you have few properties same, then will it make us isomorphic? No. Remember one thing. Very simple point. Very simple point. Actually, this is not required for the GATE exam, but this is quite intuitive. This is quite intuitive. I'm just telling you that. I'm just telling you, if you have structure A, B, you have structure A, B. Now, I'm telling you that if A is isomorphic to B, then properties will be same. Then they will have same properties. Then they will have same properties. Then they will have same properties. But remember, same properties does not mean isomorphic. I hope this point is clear. If two structures are isomorphic, then they will have same properties. But if they have same property, if you have same property with someone else, then that does not mean you are isomorphic. For example, if two structures are isomorphic, if these are isomorphic, then Both will be commutative or both will not be commutative. If A is commutative, then B will be commutative. If A is not commutative, then B will not be commutative because they will have same property. But remember, if two structures are commutative, this is commutative, this is commutative, that does not mean they are isomorphic. That does not mean they are isomorphic. So very simple. I am just telling you that if two structures are isomorphic, then they will have same property. But if they have same property, that does not mean isomorphic. But one thing interesting you can say, what is that? If different property, then what you can say? A comma B, you have structure A comma B. If they have some different property, for some property, if they have different property, if a different property, then definitely they are not isomorphic, right? If they have different property, then definitely they are not isomorphic. If they have different property, then definitely they are not isomorphic. Very simple. Okay, let's move on now. Now let's solve this question. Okay, so let's solve it. This question let's solve. So the question is asking, find the binary operations that are isomorphic. Let's see. First of all, you tell me. Okay, let's check. One by one, let's check. What is this template? What is this template? Only just focus on the template. What is this template? What is this template? In this template, can you notice what is happening? There is an element, for example, okay, let me tell you. Is this a group? Tell me, is this a group? Let me know. Is this a group? Is this a group? A, B. This is not a group. You can easily notice. This is not a group. This is not a group. Okay, because you can see this is not a group. Because you can see this is the repetition. There is a repetition in the first row. In the first row, there is repetition. So this is not a group. Okay. What about this one? What about the second one? What about the second one? Is that a group? This is also not a group. This is also not a group. What about the third one? That is also not a group. That is also not a group. What about the fourth one? What about the fourth one? That is also not a group. So, okay, none of them is a group. None of them is a group. Okay, none of them is a group. So, this group thing we cannot use. What about commutative? What about commutative? What about the first one? Is that commutative? Is that commutative? What about the first one? Is that commutative? The first one, is that commutative? Means, can I say AB equal to BA? Yes, that is commutative, right? That is commutative. So I can say that is a commutative. The first one is commutative. Okay, you can easily notice the first one, that is commutative because AB equal to BA. You can notice AB equal to BA. What about the second one? Is that commutative? What about the second one? Is that commutative? The second one is not commutative. You can notice that CD is not equal to DC. So this is not commutative. Okay, now you tell me, this structure is commutative. The first structure is commutative. Second structure is not commutative. What you can say? First structure commutative, second structure not commutative. They have different property. So they are not isomorphic. Definitely they are not isomorphic. Definitely they are not isomorphic. Okay. What about the last structure? Is that commutative? This is also not commutative. This is also not commutative. So because this is also not commutative, so I can say first is not isomorphic to fourth. First is not isomorphic to fourth. Okay. What about this middle one? Is this commutative? Is this commutative? Yes, this is a commutative. Okay, this is commutative. So I can say second is not equal to, second comma 3 are not isomorphic. Okay, second comma 3 are not isomorphic, right? 2 comma 3 are not isomorphic. So option C is gone. Option C is gone. Option 1 is correct. Okay. And what about 3 comma 4? What about 3 comma 4? Yes, they are also 3 comma 4. They are also not isomorphic. They are also not isomorphic, right? 3 comma 4 also not isomorphic. The only thing, what is remaining now? What is remaining to check? We only need to check 1 comma 3. We only need to check 1 comma 3. Okay, let's check 1 comma 3. Okay, just forget about the remaining. Just check 1 comma 3. Let's check 1 comma 3 now. So now you tell me, in this one, can you notice what is the template? Just focus on the template only. Just focus on the template only. The template is like this. Can I say that this A is the, can I say here in this, can I say that A is the dominator? Like A is dominating, right? A is dominating. Can you notice A is dominating in this? What is the template? The template is like this, that A is dominating. See what I'm saying. I'm saying like this. This is your first operation. This is your first operation. You have AB, you have AB, and what is happening here? You have like something like this, AA, AB. Okay, so can I write like this, that this is like same as you have two elements such that with A, you will always get A. Yes or no? If you do operation with A, you will always get A. If you do operation with A, you will always get A. It's something like this, that you have two elements X comma Y. You have two elements X comma Y. Operation with X. Operation with X will always, whatever you put here, operation with X will be X. Operation with X will be X. Okay, and Y will be Y. This is the template. Agree with me? Agree with me that this is the template, that you have two elements. Operation with X is X. Okay, whatever you put, operation with X is X. And Y with Y is Y. The same thing is happening in this also. In this third one also, the same thing is happening. In this third also, what is happening? See, E comma F. E comma F. So you have like this, EF, FF. So can I say the same thing is happening here? Here also you can notice with F, you will always get F. Means here also the same thing is happening, that you have X comma Y. Remember here what is X? Here your X is A, and here your Y is B. Here your X is A, Y is B. Okay. And here also the same thing is happening, that with X you will get X, and with Y you will get Y. But just the point is the names are different. Here X is F, here X is F, and here Y is E. Here Y is E. I'm just telling you that same structure, but their names are different. See, the same structure, they have the same structure, but their names are different. I hope this point is clear. So you see, one is isomorphic to 3. Why? Because they have same structure. Because they have same structure. See, they have same structure. What is the structure? The structure is there are two elements. They have same structure. And what is that? That is, there are two elements. There are two elements. With X, if you do, you will get X, and Y with Y is Y. This is the structure. Can you notice both of them have same structure? Can you notice both of them have same structure? In this one, what will happen? In this one, what will happen? In this one, I can say, in this structure one, this X is equal to A, and this Y is equal to B. This X is equal to A, and Y is equal to B. And what about this one? In this structure 3, what will happen? In this structure 3, this X is equal to F. This X is equal to F, and this Y is equal to E. Okay, so very simple. The names are different, but they have the same structure. So is this point clear? 1, 3 are isomorphic. 1, 3, they are isomorphic. They are isomorphic. So I can say 1 is isomorphic to 3. Anyway, this is not in the GATE syllabus. So tell me, will you take any tension for this topic? This is a simple intuitive topic. I am just telling you the simple intuitive topic. Okay. But this is not in the GATE syllabus. Again, I am telling you. That is the reason in the question I have written. In the question I have written already. I have written. You can check it. I have already written that this is not in the GATE syllabus. This is not part of the GATE syllabus. Okay. But did you understand some idea? Some basic idea did you understand? That isomorphism means the same structure. That isomorphism means the same structure. Same structure, same properties, same behavior. Same structure, same properties, same behavior. Please tell me, did you understand? The basic idea, did you understand? This is what you need to understand, that same structure, same behavior, same properties. Same structure. Okay, this is also same, this is also same, this is also same. Same properties. So simple. If you understood, then very good. See, if you understood this question, then very good. If you understood the solution, then very good. If you did not understand, if there is any doubt, then just forget about this. Leave this question, skip this question. This question is not required for the GATE exam. That is the reason. In the question, I have written that it is not in the GATE syllabus. Okay. So if you understood, very good. If you did not understand, then forget about it. Then forget about it. Don't worry about it. Okay. But I hope you understood the intuition. Very intuitively, I told you what is happening here. Okay. So now this is question number 20 and question number 21. These two questions are remaining, right? Question number 20 and 21. Okay. So these two questions we will do in the next session. These are very interesting questions. So I want to do in the next session. Question number 20 is remaining. Question number 21 is remaining. These two are remaining, and these are actually some, I can say, good questions. These are very good questions. These are very, very, very good questions. Okay. So we will discuss them in the next session. In the next live session, only these two questions we will discuss. That's it. Okay. So one thing I want to tell you, that in this group theory quiz, we have total 21 questions, right? In this weekly quiz 16, group theory. Okay, group theory. There are how many questions? Total we have 21 questions are there. Let me tell you that these 21 questions are covering all the variety, all the variations that are possible. In the GATE exam, whatever variation they can ask you from the group theory, whatever variation they can create, okay? In the standard resources, whatever variations are available, I have taken all the variations and I have created this quiz. So in this weekly quiz 16, these 21 questions, they cover everything. So if you understand the solution of all these 21 questions, then you are expert of group theory. So far, total we have seen 19 questions. We have seen the analysis of 19 questions we have seen. Are you comfortable with these 19 questions? Please tell me. Did you understand the analysis of all the 19 questions so far? Are you confident with group theory now? Did you understand everything so far? Whatever we have seen so far, did you understand? Okay. Okay. So the remaining two questions we will solve in the next live session. Okay. Okay. Thank you.